Welcome to my fifth lab of Coursera Intro Physics. Today we'll be looking at the orbital period of Jupiter's 4 Galilean moons. Here's a lovely picture of Jupiter itself by Damien Peach. And the experiment itself is going to be looking at the orbit of Callisto in blue, Ganymede in orange, Europa in white, and Io in green, and the period it takes to orbit around Jupiter. We're going to use Python to predict the sidereal orbital period of Io, Europa, Ganymede, and Callisto, and the apoapsis of the 4 moons as well. The sidereal period is the length of a year. For example, on Earth it is 365 days, and the apoapsis is the position when an orbiting body is farthest away from its parent. The system is the 4 moons independent of each other. The time period is 15-second intervals, and the interactions, we're going to look at the gravitational forces from Jupiter and the other moons. In this experiment we primarily use Newton's second law. That is, the delta force net is delta of momentum over delta t. We also use Newton's law of gravitation. I also use a Kepler equation for determining velocity at periapsis, where v underscore k is the velocity at periapsis, the u is the parent's mass multiplied by the gravitational constant, a is the semi-major axis, and e is the orbital eccentricity. It may be worth your while googling this, but this formula is outside the scope of this course. The initial data: we have Jupiter's masses of all the moons, the periapsis of the moons from Jupiter, i.e. the closest point to Jupiter during orbit, the eccentricity of the moon's orbits, the semi-major axis of the moon's orbits, and initial positions as positioned by me. They're not entirely accurate, but they will work well enough. The initial velocities are calculated using the aforementioned Kepler formula. We have an array containing the names of the moons, which will be used later, and we insert the velocities into an array with the velocities, and using a derivation of the gravitational law, we calculate the force net at periapsis and insert this into an array here. Moving on to the heart of the simulation. For every moon, let's find the distance between itself and Jupiter. Let's then compute the force using the unit vector and the gravitational force between the two entities. Then let's move on and calculate the same information for each and every moon between each and every moon and itself. We then calculate the change in velocity, and then with this information we can calculate a new position. This information here is for storing the distance travelled, which we'll use for finding the apoapsis and the periapsis. Now, to find the sidereal orbital period, we'll divide the orbital circumference by the distance travelled by the moon divided by the number of days of the simulation, or I think more easily summed up in this formula, where d and t is actually just the average speed. Now let's run the experiment. You can now see the moons orbiting Jupiter, Jupiter being the yellow dot. We have the period of the simulation in the top right hand corner, which is 20 days, and now we have the results on the left. Now for the sidereal orbital period results. For Io we have 1.76 days, which matches that very nicely of NASA. For Europa 3.546 days, again matches NASA very nicely. Ganymede 7.142 days, matches NASA very nicely. Just note NASA do have a typo here, you can confirm this with Google. And Callisto 16.641 Earth days and 16.689. If we can compare them, the highest error we have is 0.003%, which is a very good margin. You will have more success with a smaller delta t, and this is required for accurate results. Other gravity factors such as the Sun, Saturn and other Jovian moons, that is the moons of Jupiter, not taken into account, may distort these variables slightly, but not a lot. Feel free to change the variable days in the code and run the simulation for as long as you like. Moving on to the apoapsis results. For each moon, add the magnitude of all the positions to an array performed in a while loop, then sort these arrays in ascending order, as done here in the code, and then print the first and last values of the array. I print them out here. If we put this data in a tabular format, we can compare my results to that of NASA's. And the delta between me and NASA is very, very small. Delta t of 15 seconds was used, but you do need a small delta t value here. Given the size and complexity of the solar system and Jovian moon system, I do believe these are very good results. Well, the smaller the value of delta t, the better. You can give it a shot yourself. The opposing forces from other moons and objects such as Saturn and the Sun would slow down and accelerate the moons, may account for these variables, but again, not a lot. Now what if Jupiter's mass were to increase by 10? Well, Given that the F-net gravity is proportional to mass, an increase in the mass of one object will increase the force and hence the velocity will also increase. Note that we can see this in the shorter orbital periods on the next slide. Here you can see that when we did increase Jupiter's mass by multiplying by 10, Io, Europa, Ganymede and Callisto, their orbital periods all became shorter. Give it a shot yourself by changing Jupiter's mass in my code. The resources used for this were primarily NASA and this last site here for Kepler's laws. Thank you.